6.4, nth roots. This is where we start doing all of our square roots and all different kinds of roots. Today, the nice part about today is there's some vocab in there. There's concept stuff. The nice part about today, everything is going to work out nice. Okay? They want you guys to get comfortable working with different indices. Okay, with different types of indexes, of different radicals, different roots. Alright, so that's why today everything works out nice. Alright, so here we go. First slide. Radical is another term for nth roots. Okay, so like I think I said yesterday, a radical is the general term. Okay, so I say rad a lot. Alright, now there's different types of radicals. There's square roots, which is the one you guys all know and love. It's the one that's most common. Alright, it's right there. You guys have known that for a long time now. If you look at your calculator, and if you go into the math option, and you look down at about number 4, you'll see like a square root symbol with a 3 next to it. Alright, I've seen that before probably when you do the math frac. That's a cube root. Okay, and then you can keep on going if you look in math and you look at option 5. I'm not going to pull it up, but if you look at 5, it's got this little times box and a radical sign. That just means like any root you want to do. 5th root, 6th root, 7th root, whatever. That's the difference. Okay, so we're going to increase what root we are talking about. Now, the notation to me, honestly, as much as I try not to use technical terms and helps make stuff make sense without using the fancy speak, honestly, this is one of those places where I really hammer hard about it. And I honestly don't know why. I just do. Okay? So make sure whenever you talk about, whenever I'm teaching, make sure you know these two words. Make sure you know what the index and the radicand is. Radicand's easy. It's the stuff underneath the radical. Okay, so underneath the radical is the radicand. The index is, some people call it the crack number, because it's in the crack of the radical sign. See that? Haha. Okay. The index is, without a doubt, the most important number in this chapter. If you don't understand the concept of your index and you don't understand the differences between different indices, the whole entire foundation of this chapter goes kaboom. Alright? An index tells you what type of root you are taking, whether it be square, cube, fourth, fifth, what have you. Alright? It's the most important number. If you do not write it, I will take off points.
Write what?
The index. You'll see what I mean. Okay? If you don't write the index from my problem to your answer, I will take off points. Because you're changing the radical. You're changing what type of root you're talking about. You're basically taking a cube root, turning it into a square root, which does not happen often. Okay? That index, which will be a number eventually, most important number in the rest of the chapter for sure. Okay, technical top up there, the nth root is the inverse of the nth power. Okay, so for example, if a to the n equals b, the nth root of b equals a. Some actual legit examples down here. 5 squared equals 25, square root of 25 is 5. Alright, basic, plain and simple. The reason it works is because 25 is a perfect square. Right? Okay, take it. You know, stuff you've already known, right? You've known that for years. Okay, 25 is a perfect square. I take the square root of it, it undoes it. Done. Okay? Where this increases is now we're going to go into bigger roots. Okay, so 7 cubed is 343. So the cube root of 343 is 7. It undoes, that cube root undoes that cubed power. Make sense? Okay. 2 to the 9th is 512. So the 9th root of 512 is 2. It undoes that power. It undoes the 9th power. Alright? What's up?
Are these examples in the answers?
Mm-hmm. Yeah. Like translation?
So that would be off?
Yeah. Like, so for today, the way they're going to be set up is this. Like, say I'm going to give you the cube root of 343. Like that. I say simplify. Okay? what you do your factor trees, just like you always would. You do 7 and 49, and 49 goes 7 and 7. The only difference here is that you're trying to undo what power? Since it's a cube root, you're trying to undo the cube power. Okay, square root, you're trying to undo the square power, so you need 2. Okay, that's why you always put 2 in a group. That's why we always paired them up. That's why in your homework last night you paired them up. It was because your index was 2 and you're undoing squares. Your index is 3 now. You're undoing cubes. So you need how many in your group now? 3. And that's what you look for. You look for 3 in a group. So those 3 right there. All right, the last thing on here before we actually start problems, or at least I think it's the last thing. Some of these, and this is going to come as we practice, okay? As you work these problems out, you're going to learn what these roots are, okay? So when I say I want you to know how to do quick memory roots, I mean fast, okay? There should be no question as to, in your brain, what these answers are to these, okay? And honestly, if you think about it, with the cubes, chapter 5, remember when we did sum and difference of cubes? All right, we always had to undo cube, right? What times what gave us 64? It was 4, okay? That's all you did. And I told you those numbers wouldn't go bigger than 216 back then. I want you to know the cube root of 216 is 6 still, all right? So all of this, honestly, should already be, you should already know it, really, okay? Maybe the only one you don't know is 121, which is 11. Yeah. Okay. Because if you know this, and I'm telling you guys right now, you have to know at least these, what, 19, 18, whatever that ends up being, 18. You have to know these 18. Okay. You have to know these 18, and to be honest, you probably should know most of your 2s. Okay, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. Most of those, and then 3 to the fourth. Okay, 3 to the fourth is anybody? And then anybody know? Bigger.
81.
81. Okay. You should know those. If you know those, that makes your breaking up. That makes your factor trees. That makes when we get to 6, 6 makes all of it easier. Okay. If you understand how to break these up and how these numbers work. So make sure you know this. Okay, so simplify. Now, don't read too much into it. It's one of the rare times. The square root of 16y to the 4th. You're going to break up a square root just like you've always had. Okay? And whenever you have a number and a variable underneath that radical, take them individually, piece by piece. Okay? So I'm going to show my factor tree work just to make sure everybody's comfortable. Breaking up 16 with factor trees of 4 and 4. Okay? Since I have a square root, how many do I need in my group? 2. Okay? Even though the index isn't there, for indexes, if it's not there, you assume it to be 2. It's like one of the rare places where an imaginary number is 2, not 1. Or a hidden number, rather. Okay, Chamberlain?
So you won't have to break it down more?
No, you need pairs here.
But if you break it down both to 2, would that be a pair also?
Well, yeah, then you'd have a pair of 2s and then a pair of 2s, which you multiply them back together. Okay? So as soon as you break it up where you have a pair, you can stop. All right, which is I'm going to make a point of it here in a little bit. Ron?
Is it 4, 1, cube?
I don't know. Let's find out. Everybody's cool with the 4 coming out of the radical, right? All right, so 4. How do you break up y to the 4th? That's it?
Y squared and y squared.
Y squared times y squared. Good. Which gives you a pair. Okay, so y to the 4th you can break up y squared times y squared, and there's your pair. So those y squares come out of the radical as 1. Answer? 4y squared. 9. Okay. in case you've never seen it before, that's an example of when you have an index. Okay? See the little number here? Right there? That is a powerful, powerful number. That number tells you how many factors you need in your group before you can break it into a radical. Okay? So, since you have a fourth root, you need 4 in a group. Alright? Now, you can always do this. Hang tight. Always, the safe bet is always factor trees. Every single time when you're working with radicals, your safe bet is factor trees. So that's what I'm going to do now. Alright, factor tree of y squared, and each y squared goes y and y. There's your group of y's. They come out as 1, so this simplifies down to just y.
You got the variable z, you just like automatically just do it on the side. Like you don't break it down. Like you know when you do it with a number, you just
Usually go down. It depends how many you got there, because you're going to have ones that you have like 3 terms underneath. So you got to be creative with your factor trees. One you can go down, one you can go to the side, one you might have to rewrite off to the side and do. It just depends how many terms you have. Okay, Maria?
Why did you break up those y squareds, but on the last problem you did?
Because the last one we had an index of 2, so we needed a pair. Here we have an index of 4, right there. That 4 right here.
Yeah.
So that tells me you need 4 in your group before you can circle them. Okay, that's what that number, the finger stay. That's what that number tells you. It tells you how many you need in your group before you can bring that group out as 1. All right, Lydia.
What if you don't have 4?
Then you're an issue. Then you got an issue because then you got stuff either left over or extras.
Is it always going to be like this?
Today they'll be even. Okay, but like how the number 3 had that leftover x, that's that case. It just stays inside. Okay. Right, Sam.
I didn't see that next one.
It wasn't there. If it's not there, you assume it to be a square root, and you assume it to be 2, just like it always has. Okay. Everybody good? So one way with this is factor trees. Anybody? I'm not going to say it's true all the time, but does anybody notice something?
the index and the exponent is the same.
Okay. And then what was our results exponent? 1. Okay.
So if they're the same, it's going to be 1. You can divide it?
Maybe. Let's hang tight. Okay. I'm not going to say yes or no yet, but let's see how this works out.
That'd be 0.
No, 4 minus 4?
Y to 0.
Is
That'd be 0.
so the logic is divide. Okay, but I'm not going to say for sure yet. All right.
So then it'd be 2, since there's nothing right there.
Okay. So see, yes. Okay. So see how this one doesn't have an index? So it's just a regular old square root. You go back to your pairs. Okay. I purposely did this. Do 1 squared, do 1 not, do 1 squared, just so you guys got to get to the mindset. Okay. The first number you should check with a radical is the index, because that tells you so much. Okay. Lip. 6y to the 3rd with such enthusiasm.
Okay.
The square root of 36, you guys know, is 6. Okay. You got to break it up into trees. There it is. 6 and 6. There's your 6. Y to the 6 breaks up.
Y cubed and y squared.
Y cubed.
Y squared.
Y cubed. Because you add the exponents. Remember that factor trees make multiplications. Okay? Because you're multiplying there. Okay? And when you multiply your bases, you add the exponents. Okay? So, because remember, you're dividing them out to break them up, right? How we divided 36 by 6 to get 6 here? Remember that? Okay? Same thing with your exponents. Same thing with your variables. Except you have to take into account your exponent rules. Chapter 5. Okay? Because if we're going to put these back together, we're going to do it with multiplication, right? And y to the 3rd times y to the 3rd gives you y to the 6th. So you have to take that into account with your variables because you have to account for your exponent rules.
So you're basically saying with the y's is like what adds the at equals 6. Like you're just adding it.
more or less. Okay. Shortcut type people, have we noticed something this time too? Yeah? Okay, Lift is back there. Okay, let me actually write the answer down. I didn't do that yet. 6 y to the third. I won't say it's true yet though. Still not yet. Ready for the next one?
Yeah.
This one's all you. Hit it.
Yeah.
So do 243 with 3 and 81. 81 goes 9 and 9. The 9s go 3, 3, 3, 3. You need your index is 5. See that? So you need 5 3s before they come out as 1 3. Okay. Now, maybe we're getting just a little bit better with this, okay? So if I need groups of 5, okay? And if I have 20 A's, how am I going to figure that out? Divide by 5.
Just to save it.
Okay.
Trouble.
Just to save you the trouble.
But if you can't,
Okay?
For all of them, you can do it?
Yes. So what's 20 divided by 5?
4.
4. The exponent on A is 4.
Hold up. Hold up. These exponents. Okay.
Okay.
So, with 20,
Yeah.
I want to do 2 and 10.
No, because you
I
have to
do
add,
10.
because you do 10 and 10. Right.
So for
And
25.
Then that break down to 2 and 5 and 2 and 5.
No, you're still, hold up.
Oh, I'm still.
You're still doing it. Yep. A to the 20th, you would go
I keep on forgetting.
A to the 10th.
Why,
A
why
to the
is it
10th.
switching?
Because these are variables. Okay. Remember what we're doing? Multiplying them back together once you break a factor tree, right?
Mhm.
So what's A to the 10th times A to the 10th?
20.
20, because you add the exponents.
Mhm.
So whenever you break them up, you have to subtract them.
Right.
Okay? So when you do A to the 10th, here, you do A to the 5th,
A to the 5th.
or A to the 5th. Or you can do any combination. All right? That first factor tree does not have to be A to the 10th, A to the 10th. Okay?
I'm still not understanding where you get 4 from. Because if both of those break down to 5.
How many pairs of
Yeah, would you keep going 2.5?
Chamberlain, hang on. I'm going to blow your mind. Ready? I'm going to blow your mind. I'm going to make a 5-leaf factor tree.
5.
we did?
Okay? In each one of these leaves, I'm going to put an A to the 4th. All right? Now, remember what I said? To put a factor tree back together, you do what? Now, you multiply the bases, which means you do what with those exponents? You add them. So what's 4 plus 4 plus 4 plus 4 plus 4? 20. Okay? And what's my index?
5.
So I need a group of 5. There they are.
You do 25. Like,
Okay? Makes sense.
I just, if you can divide, then I just want to know
That's
how would you do it,
exactly-
breaking it down.
That's exactly it. Okay? And that's all I did. I made a 5-leaf factor tree, which gives me the fourths. Okay? So it's just as quick to divide the index into the exponent.
Okay.
Okay? Rainey, you were first.
Do you have to make a factor tree?
You don't have to.
Because
You don't have to. Okay?
the fifth is like in the 3,000, so
Correct. Correct.
so nice.
Right. You don't have to make factor trees with these today because they are going to work out even. Once we get going with more of these, I'm not going to either. Okay? Ron?
PD number 25. Okay, explain. I don't know how.
Yeah, hold on a second. Jazz?
What word do we use to show for these?
Not much. At all.
Like I just skip the
Yeah.
little factor tree thing?
Yep. Okay. So B to the 25th, you still need groups of 5. Okay? So if you have 25 B's and you want to group them into 5, how many groups do you have? 5. So your exponent on B is B to the 5th. Same logic factor tree wise. Okay? Where the mindset has to change is your variables aren't numbers. Okay? And when you multiply the variables together, you add up those exponents. That's where the mess becomes. Okay? Because you're adding 4 with 4 with 4 with 4 with 4 to get one group of A to the 4s. You're adding 5, 5, 5, 5, and 5 to get one group of B to the 5ths. Okay? So your numbers, you have to break up with factor trees. Okay, like here. Your numbers, your legit numbers. Your variables, you can take the exponent divided by the index and get the answer that way. All right? Everybody good so far? All right. But now what? The square root of x squared minus 6 to the 8th power. All right, now I'm going to right now explain this, okay? Now, you are taking the square root. What are you taking the square root of? One person. You are taking the x square root of x squared minus 6 as a quantity to the 8th power. So, how many x squared minus 6's do you have? 8. You have 8 x squared minus 6's. How many do you need to put in a group? 2. So you have 4. The only exponent that you give a crap about is the outside one. Okay? This one out here on the binomial, right there. That's the only one the square root affects. It does not affect the x squared. It does not affect the 6. Because they're inside the quantity that you're taking to the 8th power, that is therefore being square rooted. Okay? If you were to get really technically super involved with this, you could factor tree this out. Right? And I'm only doing this one time since it's only a square. X squared minus 6 to the 4th. X squared minus 6 to the 4th. There's your pair.
For real?
For real. Okay? You remember grouping? Okay? Remember grouping when I first introduced it to you guys and I said you got to change your thinking about what a term is? Okay? And I said you got to think of the whole thing as a term and the other thing as a term, and you have a binomial as a GCF. Okay? You got to change that mindset here too, because you're taking the square root of the binomial that's to the 8th power. This could be anything in here. Okay? This can be anything. Alright? And I'm going to show you a quick example because I want to make sure we get to the last type. Alright? Hold on.
When you get to a point where you have to factor out the exponent on the outside?
No. Okay? Here is one of my favorite questions of this chapter from a challenging standpoint. The cube root of x cubed minus 27 to the 15th power. Okay? X cubed minus 27 to the 5th. That's it. Okay? The cube root affects that big exponent. That's it. Because you're taking the cube root of that quantity. Okay? Now, why do you think people mess that up all the time? What's in there? What's Mormon being a sneaky son gun about?
You seen that too?
Oh, x cube's a perfect cube, 27's a perfect cube. Oh, yeah. I see a lot of x minus 3's to the 5th. Okay? You only do it to the big power when you have a binomial inside. Okay? Makes sense?
Wait, what's the answer for that?
That would be x cubed minus 27 to the 5th.
Oh.
Okay? Everybody good? Lip?
I wasn't wrong. 6 to the 4th is 1,296. So wasn't that technically right too?
These last two, if you notice, have what going on inside the radical? One operation. Between the two things, between the two terms. Multiplication. Okay? You have a multiplication going on. Alright? Now, sorry for those that are writing, I'm backing up just a few. On here, what was going on between the 36, I know we didn't do this, But what was going on between the 36, the x, the y, and the z? What operations? Multiplication. All right. Just like how there was multiplication going on here, and not there, and there. Okay? Yeah. And whenever we did, let's go back here real quick. When we did multiplication with this one, you treated each one what? You did the 243 separate. You did the 243 by itself. You did the 8 to the 20th by itself. You did the b to the 25th by itself. Here, you just had three monomials, or three terms, three separate things, right? A number and two variables. All multiplied together, you took them separately. Here, you have a number and a binomial being multiplied together. You still take them separately, though. Okay? Do the 6th root of 64. Do the 6th root of x squared minus 3 to the 18th power. All right, here we go. Let's finish up. Take 64, you break it up, okay? Now, like I said, know your 2's, okay? Know your 2's, especially know 64. 64, once we get into this section, 64 is one of my favorite numbers. It's 8 squared, it's 4 to the 3rd, it's 2 to the 6th, okay? So it's 2 to the 6th. So you have 6 2's in there, it comes out as a 2. You keep the binomial just like it was, x squared minus 3. And you need them in groups of 6, which leaves you with how many, Ron? 3, very good. Okay? Individually, number and binomial, just like you did numbers and variables. Okay? Number 9, 16 has 4 2's in it, so there's your 2. X minus 3, also to the 3rd. I got pretty lazy back here on this.
How is that 2?
4 through to 16. 4 and 4. Each 4 goes 2 and 2. So you got 4 2's. Okay?
4 going to 16. Oh,
No,
so
I know it's 4 and 4. 2. But don't you gotta...
You need groups. You need a group of 4.